Hello, everyone. Welcome to Sleep Space. Tonight, we will talk about one of the strangest, most mind bending questions in all of cosmology. What is the universe expanding into? If scientists say the universe is expanding, then what is it stretching out into? Is there some kind of void beyond the edge of space, a giant black nothingness waiting to be filled? Or is there no outside at all, just more universe in every direction? This is the paradox of an expanding universe with no edge, and it has puzzled scientists and philosophers for decades. Before we begin, I'd love to know what you think. What do you imagine when you hear the phrase, the universe is expanding? Do you picture galaxies moving apart in an infinite black void? Or maybe the universe like a balloon being inflated? Share your thoughts, and while you're at it, let me know where you're watching from tonight. To start unraveling this, we need to go back to the beginning, or at least as far back as we can. About 13.8 billion years ago, the universe as we know it emerged from what we call the Big Bang. Contrary to the popular image, the Big Bang wasn't an explosion that happened at some particular spot in space. Instead, it was the sudden appearance of space and time itself. The Big Bang didn't happen in one corner of the universe. It happened everywhere at once. Space expanded, carrying matter and energy along with it, and it has been expanding ever since. This is where the first big misconception often comes in. When people hear expanding universe, they naturally imagine an explosion in an empty room. You picture debris flying outward into the surrounding emptiness. But cosmologists tell us that's not what's happening. The universe isn't expanding into something else, it's expanding into itself. The expansion means that the fabric of space itself is stretching. Galaxies aren't flying through some external void. Rather, the distances between galaxies are increasing because space itself is growing. That idea can sound almost nonsensical because we're so used to the way things expand in our everyday lives. A balloon expands into the air around it. A drop of ink spreads into water. But the universe doesn't have air or water or some kind of cosmic container surrounding it. When cosmologists say the universe is expanding, they mean that the metric that defines distance is changing. If you were to imagine a grid laid over the universe, the spacing between the grid lines is getting larger over time. One of the most useful analogies is that balloon example I mentioned earlier. Imagine dots drawn on the surface of a balloon. As you blow up the balloon, the dots all move farther apart from each other. From the perspective of any single dot, it looks like all the other dots are receding. But here's the catch. The surface of the balloon represents the universe in this analogy. It's two-dimensional, but it has no edge. You can walk around the surface forever without finding a boundary. The expansion doesn't require the balloon to expand into a larger three-dimensional room. At least, not in the analogy itself. Instead, the surface is expanding in terms of its own geometry. Now, our universe isn't the surface of a balloon, but it may be similar in that it can expand without expanding into anything. This is hard for our brains to accept because we evolved to understand objects inside space, not space itself. You've never seen space stretch in your daily life, so it feels alien. But astronomers have evidence that this is happening. The light from distant galaxies is shifted toward longer wavelengths, what we call redshift. This redshift increases the farther away a galaxy is. That's exactly what you'd expect if space itself is stretching, pulling the galaxies apart. So what does this mean for the idea of an edge? If space is all there is, then there's no outside. Asking, what is the universe expanding into? Maybe like asking, what's north of the North Pole? The question assumes a framework that doesn't apply. The universe may not need an outside in order to expand. Instead, expansion is simply a property of the universe itself. But let's not stop here, because cosmology isn't content with simple analogies. It digs deeper. Some models suggest that our universe may be finite but unbounded. Imagine a video game world where walking far enough in one direction eventually brings you back to your starting point. There's no edge, but it's not infinite either. Mathematicians call this kind of shape closed. If our universe is closed, then space is wrapping around itself. Expansion, in that case, would mean that the size of this closed geometry is increasing, again without needing anything outside it. On the other hand, the universe may be infinite. If space is infinite, then it always was infinite, even at the Big Bang. In that case, expansion doesn't mean that infinity is getting bigger. Instead, it means that any 2 points in this infinite fabric are getting farther apart. Infinity remains infinity, but the density of matter within it changes over time. This scenario is even harder to visualize, but it may very well be true. Let's pause and reflect here. You live inside a universe that is getting larger with time, yet has no edge and no outside that it's expanding into. Space itself is stretching. Time itself is flowing forward. And you, right now, are sitting inside this expanding reality, carried along with every other galaxy and star. You don't feel it because the expansion only matters at enormous scales. The atoms in your body aren't being pulled apart. Your house isn't growing with the cosmos. Gravity, electromagnetism, and nuclear forces keep small systems bound together. Expansion only dominates at the scale of clusters of galaxies. Now, here's another way to look at it. Imagine you're an ant living on that balloon surface. You can measure distances between dots, and you'll find they grow over time. You'll conclude that the surface is expanding, but unless you're able to step into a higher dimension, which you can't, you won't ever see the balloon as a whole object. The expansion is simply part of your two-dimensional world. In the same way, we may never be able to perceive outside the universe, because outside might not exist. But then the question becomes, why is the universe expanding at all? What set it in motion? In Einstein's general theory of relativity, space and time are dynamic. They can bend, stretch, and evolve in response to matter and energy. According to this theory, the equations naturally allow for an expanding or contracting universe. In fact, Einstein originally tried to resist this idea by adding a cosmological constant to his equations, trying to hold the universe static. But when Hubble discovered that galaxies were moving away from us, the evidence for expansion became undeniable. And here's the twist: expansion isn't slowing down. In the late 1990s, astronomers studying distant supernovae discovered that the expansion of the universe is accelerating. Something is driving galaxies apart faster and faster. We call this mysterious something dark energy. We don't know what it is, only that it makes up about 70% of the energy content of the universe. If dark energy continues to dominate, then the universe will expand forever, becoming colder and emptier with time. So let's circle back to the question we began with. What is the universe expanding into? According to the best scientific understanding, it's not expanding into anything. The expansion is simply the growth of space itself. The into part of the question might not make sense, because space doesn't need an external stage to grow upon. The universe is the stage, and yet it's natural to keep asking the question, because our minds crave an outside, a boundary, a place beyond. Some theories even entertain the idea of a multiverse, that our universe is one bubble among many, floating in some higher dimensional space. In that scenario, maybe our universe really is expanding into something larger. But if that's true, then whatever that larger space is, it's not observable from within our universe. For now, expansion without an outside remains the most accepted explanation. As we continue, we'll dive deeper into how cosmologists test these ideas, how geometry and relativity shape our understanding, and what this means for the ultimate fate of the universe. But for tonight's beginning, just sit with this thought. You are living inside a cosmos that is constantly stretching, not into emptiness, not into another place, but into itself. It's a reality that bends the way we normally think. But it's also what makes the universe so astonishing. When you hear that the universe has no edge, it can feel like a riddle designed to frustrate the human mind. We are conditioned to think in terms of boundaries. A cup holds water, a balloon holds air, a room is enclosed by walls. If you walk to the edge of a field, there's a fence. If you cross the ocean, eventually you find land. But the universe plays by different rules. The universe is not contained within anything, and that's the heart of why expansion seems paradoxical. Let's take a step into the math for a moment, because the mathematics of cosmology gives us a language to describe what words often struggle to capture. At the core of modern cosmology lies general relativity. Einstein's theory that describes gravity not as a force pulling objects together, but as the curvature of spacetime itself. According to Einstein's equations, the universe as a whole doesn't have to be static. In fact, the default solutions predict expansion or contraction. The geometry of space evolves over time depending on the amount of matter, energy, and curvature it contains. That means expansion isn't some extra phenomenon layered on top of the universe. It is built into the structure of spacetime itself. When we say galaxies are moving apart, it's not like dots flying away through pre-existing space. Instead, the ruler we use to measure distances is itself changing. Distances that used to be 1 billion light years across might become 2 billion light years simply because the grid of space is stretching. But even when you understand this mathematically, the question of what lies outside still creeps back in. Our imaginations struggle to picture something growing without an exterior. Let's revisit the balloon analogy, but push it further. If the surface of the balloon is all you can access, then you never see the air around it. To you, the balloon's surface is everything. If the balloon doubles in size, the surface grows, but there's no edge on the surface itself. In the same way, the universe might be self-contained, needing no external dimension to expand into. However, this leads to a fascinating possibility. What if there are dimensions beyond what we perceive? In string theory and other speculative models, our universe may be a three-dimensional brain, floating inside a higher dimensional space. If so, then expansion could, in principle, be described as growth within that higher framework. This is where the idea of a multiverse comes in. Perhaps there are countless other universes, each with their own expanding spacetimes, coexisting in a larger reality. But right now, these are untestable ideas. Science demands evidence, and evidence for other universes remains elusive. Now let's consider what expansion actually looks like from our point of view. When Edwin Hubble and his colleagues looked at distant galaxies in the 1920s, they found something remarkable. The farther away a galaxy is, the faster it appears to be receding from us. This relationship is now called Hubble's law. If the universe were static, you would expect galaxies to move in random directions, pulled by local gravitational forces. But instead, there was a systematic trend. Every distant galaxy was redshifted, meaning its light was stretched to longer wavelengths. This redshift wasn't because galaxies were racing away through space, but because space itself was expanding, stretching the light as it travelled. Think of light waves like ripples in a rubber band. As the band is pulled, the ripples stretch out. The universe works the same way. The more the light travels, the more it gets stretched. This is why the most distant galaxies appear the reddest. This discovery forced a radical shift in how scientists viewed the cosmos. Before Hubble's work, the dominant belief was that the universe was eternal and unchanging. The stars we see had always been there. Space was a fixed stage on which events unfolded. Expansion shattered that idea. Suddenly, the universe had a history. If it was expanding now, it must have been smaller in the past. Trace it back far enough, and you reach a moment of origin, the Big Bang. But even here, there are subtleties. The Big Bang wasn't an explosion in space, it was the expansion of space itself. This is crucial. When you think of an explosion, you imagine a fireball with fragments flying into empty air. That's not the case here. Instead, the Big Bang was the beginning of space and time. Asking what came before or what was it expanding into is tricky because time itself began at that moment. There was no before in the conventional sense and no outside for it to expand into. To get an intuitive feel for this, let's explore a simple metaphor from geometry. Picture a circle drawn on a sheet of paper. That circle is one-dimensional. You can walk along it forever without reaching an end, yet it has a finite circumference. Now imagine inflating the circle into a sphere. The surface of the sphere is two-dimensional and closed, but unbounded. You could travel around it indefinitely without encountering a wall. If the sphere expands, the surface grows larger, but you don't need an outside to explain the expansion. The expansion is simply the increase in the geometry of the surface itself. In cosmology, the universe could behave in a similar way, except in 3 dimensions of space instead of 2. There's another fascinating concept to bring into the picture: cosmic inflation. This is the idea that in the earliest fractions of a second after the Big Bang, the universe expanded exponentially faster than the speed of light. Within less than a trillionth of a second, space ballooned from subatomic scales to cosmic scales. This theory was developed to explain some puzzles, like why the universe looks so uniform in every direction, and why space appears flat rather than curved. Inflation theory suggests that the part of the universe we see today is just a tiny patch of a vastly larger whole. If that's true, then our observable universe might be like a small island in an ocean of space we'll never see. Expansion, then, isn't just about what we can observe. It might be happening on scales far beyond our cosmic horizon. Speaking of horizons, that's another key part of this story. Just as the Earth has a horizon beyond which you can't see, the universe has a cosmic horizon. Light from beyond a certain distance hasn't had time to reach us yet, because the universe has a finite age. Right now, that horizon is about 46 billion light years away in every direction. That defines our observable universe, but the universe as a whole may be much larger, possibly infinite. When we talk about the universe expanding, we're referring to this observable patch, but the real expansion might extend far beyond what we can detect. This is where we need to distinguish between two concepts: the observable universe and the entire universe. The observable universe is bounded by the speed of light and the age of the cosmos. It's the region we can study with telescopes. But the entire universe might have no bounds at all. Expansion doesn't stop at the edge of the observable region. It continues everywhere. The difference is that we just can't see beyond our cosmic horizon. It's tempting to imagine that if you could somehow travel fast enough, you'd reach an edge. But the edge isn't a wall or a boundary. It's just the limit of what light has been able to show us so far. If you could somehow wait infinitely long, more of the universe would come into view. But because expansion is accelerating due to dark energy, some regions will forever remain out of reach. In fact, over the next trillions of years, distant galaxies will drift so far away that their light will never reach us, no matter how long we wait. Our cosmic horizon will shrink in terms of visible galaxies, leaving future civilizations with a much lonelier view of the universe. Now let's step back and appreciate the scale of this. You live on a small planet orbiting an ordinary star in one galaxy among billions, and all of these galaxies are being swept along by the expansion of spacetime. Yet you can't feel it happening. To you, the ground beneath your feet feels stable. The expansion is imperceptible locally because gravity holds the Earth together, the solar system together, and even our galaxy together. The Milky Way isn't being pulled apart. It's bound by its own gravity. The expansion only shows itself in the vast distances between galaxy clusters, where gravity is too weak to resist it. This leads to a subtle but important realization. Expansion isn't about things moving through space. It's about space itself evolving. The grid lines of the universe are stretching, and everything embedded in that grid is carried along. That's why there's no central point of expansion. Every galaxy sees every other galaxy receding. If you lived in a distant galaxy, you'd conclude that the universe was expanding away from you too. There is no privileged center. Expansion is universal. The more you think about this, the more it bends your sense of reality. Our daily experiences train us to expect edges, outsides, and boundaries. But the universe doesn't conform to those expectations. Expansion without an exterior is possible because space is not a thing inside something else. It is the stage itself. And this stage is dynamic, capable of growing, stretching, and reshaping itself with time. The more we study the expansion of the universe, the more we realize it challenges not just physics, but the very way we think. Our minds are wired to imagine objects within space, but here we're forced to imagine space itself changing. It's not something you can hold, point to, or observe directly. You can only see its effects: galaxies drifting apart, light stretching across the cosmos, the echoes of the Big Bang still humming in the microwave background radiation. One of the most striking discoveries of the 20th century was that the universe is homogeneous and isotropic on large scales. Homogeneous means it looks the same in every region. Isotropic means it looks the same in every direction. No matter where you point your telescope, the distribution of galaxies and the glow of the cosmic microwave background appear remarkably uniform. This is part of what convinced scientists that the expansion isn't happening from a particular point into some larger void. It's happening everywhere at once. Imagine baking a loaf of raisin bread. As the dough rises, every raisin sees every other raisin moving away. From the point of view of any single raisin, it looks like expansion is happening outward from them. But really, the dough itself is swelling. This bread analogy is closer to the truth of what we live in. You are a raisin in the cosmic loaf. Expansion is not about raisins flying through empty air. It's about the dough stretching. But if the universe has no center and no edge, then what exactly defines its shape? This is where cosmology gets deeply mathematical, because the geometry of the universe is determined by its energy content. According to general relativity, matter and energy tell space how to curve, and space tells matter how to move. The interplay between them defines whether the universe is flat, open, or closed. A closed universe is like the surface of a sphere. Travel far enough in one direction, and you eventually circle back to where you began. An open universe is like a saddle, curved outward, infinite, and ever expanding. A flat universe is like an infinite plane with no curvature at all. The remarkable thing is that current measurements show our universe is very nearly flat. The cosmic microwave background, mapped by satellites like WMAP and Planck, reveals that the geometry of the universe is astonishingly close to zero curvature. This suggests that the universe might be infinite in extent, or at least so large that it appears flat to us within the observable horizon. This flatness introduces another layer to our question. If the universe is infinite, then it doesn't expand into anything. It simply stretches, with distances between objects increasing forever. Infinity doesn't grow in size, but the scale factor that defines distances grows. It's like multiplying infinity by 2. It's still infinite, but everything inside is more spread out. But even if the universe is infinite, we are confined to a finite view. The observable universe, limited by the speed of light and the age of the cosmos, is like a bubble around us 46 billion light years in radius. This bubble defines what we can see, but it is not a boundary of the universe itself. Expansion doesn't stop there. Beyond our horizon, more galaxies exist, more space stretches, more reality unfolds. The paradox of no edge remains, because the horizon is not an edge. It is just a limit of our perception. Let's bring in another fascinating concept, the cosmic microwave background radiation, or CMB. This is the afterglow of the Big Bang, the faint radiation left over from when the universe was about 380,000 years old. Before that time, the universe was a hot plasma of particles and photons, opaque to light. Once it cooled enough for atoms to form, light could travel freely. That ancient light still reaches us today, stretched into microwaves by billions of years of expansion. The CMB is a powerful confirmation of the expanding universe. Its uniformity across the sky shows that the cosmos was once much smaller, denser, and hotter. But its tiny fluctuations, the subtle hot and cold spots, encode information about the geometry and contents of the universe. When cosmologists measure these patterns, they find that the universe's expansion is consistent with general relativity, dark matter, and dark energy. The CMB, in other words, tells us that the expansion is not an illusion. It is written into the background glow of the universe itself. Now let's wrestle with a different version of the question. If the universe is expanding, does that mean space is being created? The answer is yes, sort of. Space isn't a substance being manufactured, but the distances between points are increasing. You can think of it as new room constantly appearing between galaxies. This doesn't violate any conservation laws because space itself isn't a material. It's the stage on which physics happens. The amount of matter and energy is finite, at least in the observable region, but the size of the stage keeps increasing. There's also the counterintuitive fact that galaxies can appear to move away from us faster than the speed of light. At first, this seems impossible, since relativity tells us nothing can travel faster than light. But relativity only forbids objects from moving through space faster than light. When space itself expands, there's no such speed limit. A distant galaxy doesn't have to move through space at all. The space between us and it simply stretches. As a result, many galaxies are already receding faster than light. Their light will never reach us. Expansion is so powerful that it can outpace even light itself. This brings us to the idea of cosmic horizons once again. Right now, our observable universe includes everything from which light has had time to reach us since the Big Bang. But because expansion is accelerating, there are regions we will never be able to observe, no matter how long we wait. The observable universe is shrinking in terms of what we can access in the future, even as the whole universe grows. Over trillions of years, only the nearest galaxies bound to the Milky Way will remain visible. The rest will fade into darkness, forever beyond reach. Now think about the philosophical implications. If the universe has no edge, then it has no outside for us to point to. But if it is infinite, then it has always been infinite. This stretches the imagination. How can something have always been endless? even at the Big Bang? The answer lies in understanding that expansion doesn't require an external container. The Big Bang happened everywhere at once, not at a point in space. Infinity doesn't need to grow, it simply evolves. But then there's the possibility of a finite universe. Suppose space is closed, like a three-dimensional sphere. Then the universe could have a finite volume, but still no edge. Expansion would simply mean the radius of this higher dimensional sphere is growing. In that case, asking what lies outside is meaningless, because the surface itself is all there is. There is no external space to expand into. And yet, human imagination keeps returning to the multiverse. If inflation theory is correct, our universe may just be one bubble among many. Each bubble universe could have its own physics, its own constants, even its own number of dimensions. If that's true, then our universe's expansion might be part of a larger story, one bubble swelling in a cosmic sea of bubbles. The problem is that we cannot observe beyond our own bubble. Whether the multiverse exists remains speculation. For now, science confines itself to the observable universe and the laws we can test. What we can say with confidence is that the expansion is real, measurable, and ongoing. Every photon of ancient light carries its signature. Every distant galaxy drifting away reinforces the pattern. The paradox of expansion without an edge is not a flaw in our understanding. It is a feature of how space-time itself behaves. It is our perspective that struggles, because we are creatures evolved to navigate fields and forests, not infinite cosmologies. If we're going to truly grasp the idea of an expanding universe with no edge, we need to slow down and look carefully at what space actually means. In daily life, we treat space as empty room, the nothingness between objects. But in physics, space isn't a void. It's part of the very fabric of reality. It has properties, it can bend, stretch, ripple, and interact with matter and energy. When we say the universe is expanding, we're talking about this fabric itself changing over time. This is why scientists often caution against visualizing the universe as a bubble in a black void. That picture sneaks in an outside which may not exist at all. Instead, the universe is self-contained. You don't need an external nothingness for space to grow, because space is not a thing inside something else. It is the geometry of reality. The mathematics of general relativity describes this geometry precisely. Distances between objects increase because the metric, the mathematical function that defines distance, evolves. But let's get concrete. How do we know the universe is expanding? We can't see space stretching with our eyes, but we can see what it does to light. As light travels through space, it gets stretched along with it. That stretching shifts its wavelength toward the red end of the spectrum. The farther away a galaxy is, the more stretched its light becomes. This systematic redshift is one of the strongest pieces of evidence for expansion. Without the concept of expanding space, the pattern of redshifts would be inexplicable. Even more persuasive is the discovery of the cosmic microwave background radiation, the leftover glow from the early universe. This faint radiation fills the sky in every direction. Its uniformity, combined with tiny fluctuations, confirms that the universe was once extremely hot and dense before expanding and cooling. If expansion weren't real, we wouldn't see this ancient light stretched into the microwave spectrum. The CMB is, in effect, a fossil of expansion. And then came the discovery that truly changed everything: the acceleration of expansion. For decades, scientists assumed gravity would slow expansion down over time. Maybe it would halt eventually, or even reverse, leading to a big crunch. But in the 1990s, observations of distant supernovae revealed the opposite. Instead of slowing, the universe is speeding up. Expansion is accelerating, as if some hidden energy is pushing everything apart. We call this mysterious driver dark energy. We don't know what it is, but we know it dominates the universe. Roughly 70% of the cosmos is made of this unknown force. Dark matter makes up about 25%, and ordinary matter, the atoms in stars, planets, and people, accounts for less than 5%. In other words, most of the universe is invisible and mysterious. And yet, it is this invisible energy that determines the future of expansion. Now, let's think about what this means for the fate of the cosmos. If dark energy continues to drive accelerated expansion, then galaxies will drift farther and farther away from each other. Eventually, the night sky will grow darker as distant galaxies fade from view. Over unimaginable timescales, only our local group of galaxies, gravitationally bound together, will remain visible. Expansion will make the universe a lonelier place. But there are other possibilities. Some versions of dark energy could change over time. If it grows stronger, the expansion could tear apart galaxies, stars, even atoms themselves in what's called the Big Rip. If it weakens, gravity might eventually overcome it, leading to a collapse. Right now, the data favors a steady dark energy that keeps expansion accelerating forever. But the future is still uncertain. This brings us back to the heart of our paradox. If the universe is expanding forever, what is it expanding into? The best answer remains nothing. The expansion isn't into a pre-existing void. It's the distances themselves increasing. There is no outside. The universe is all there is. But our minds keep resisting this. We want to imagine edges, containers, or boundaries. We ask what's beyond the horizon, what lies past the last galaxy. And here's where philosophy meets physics. Some thinkers argue that the question itself is flawed, because outside the universe is a nonsensical concept. The universe is defined as everything that exists. Asking what's outside it is like asking what's beyond everything. By definition, there is nothing else. Expansion doesn't require an external backdrop. It is an internal feature of existence. But human imagination doesn't stop there. Some scientists and philosophers speculate about higher dimensions. If our universe is a three-dimensional brain floating in a higher dimensional space, then maybe it is expanding into that space. Maybe our Big Bang was the result of two such brains colliding. In such a scenario, the universe does expand into something larger. But this is speculation, not confirmed science. Without observational evidence, it remains in the realm of hypothesis. Even so, these speculations show how deeply unsettling expansion without an outside feels. We are creatures used to boundaries. Our maps have edges. Our houses have walls. Our lives are defined by beginnings and ends. The universe challenges all of that. It tells us that space can expand endlessly, with no boundary, no center, no edge. That everything we see is part of a larger whole that may stretch forever. This is why analogies are so important. The balloon, the raisin bread, the video game world where walking far enough brings you back to the start. All of these help us glimpse the possibility of an unbounded space. They're imperfect, but they nudge our minds toward the truth. Expansion doesn't need an exterior. Space itself can grow without moving into anything else. Another way to picture it is through mathematics. Imagine a coordinate grid on graph paper. If you increase the spacing between the grid lines, every point on the grid moves farther from every other point. Yet the paper itself hasn't expanded into a bigger desk. The expansion happens entirely within the grid's own geometry. That's what cosmologists mean when they say the universe expands. Still, there's an itch that won't go away. If expansion is happening, what set it in motion? Why did the universe begin to grow in the first place? The answer seems to lie in the physics of the Big Bang and inflation. Inflation theory suggests that quantum fields in the earliest instant after the Big Bang triggered a burst of expansion. Once that field decayed, expansion slowed, but it never stopped. The momentum of the Big Bang carried space outward, and dark energy now fuels the acceleration. Expansion, in other words, is written into the very birth of the universe. There's another wrinkle to consider: quantum mechanics. On the smallest scales, reality is governed by uncertainty. Particles flicker into and out of existence, fields fluctuate, and energy cannot be precisely pinned down. Some physicists suggest that the entire universe could have emerged from a quantum fluctuation. If that's true, then expansion is not just a feature of our universe. It could be a feature of many universes. A multiverse of inflating regions, each bubbling into existence, each expanding forever. For now, these remain speculations. What we can say with certainty grounded in observation is that our universe is expanding. It has no edge, and it is not expanding into anything. That answer may feel incomplete, but sometimes reality doesn't conform to the categories our minds expect. Space itself is the category. Space itself is the framework. Asking what it expands into may be like asking what time flows into. Time doesn't flow into another dimension, it just flows. Space doesn't expand into something, it just expands. And perhaps that's the most humbling realization of all. The universe does not need to fit into our intuitive boxes. Our intuitions evolved to throw spears, build shelters, and navigate forests, not to comprehend the infinite. Yet here we are, creatures of atoms and stardust, sitting on a small rock, pondering the expansion of the entire cosmos. One of the most profound challenges of understanding the expanding universe is realizing that our usual categories of inside and outside simply don't apply. We live in a reality where the rules of geometry itself are not fixed, but dynamic. The universe is not expanding into something larger, but instead it is space itself that grows. This takes us far from our daily experience, but the evidence and the mathematics are both clear. To really appreciate this, we need to examine the difference between local space and cosmic space. Locally, expansion is negligible. The distances between atoms in your body do not stretch as the universe expands. Your coffee cup doesn't expand, your city doesn't expand, not even your galaxy expands. That's because the forces that hold these systems together, electromagnetism, gravity, nuclear interactions, are much stronger than the very slight push of cosmic expansion. Expansion is only visible on the largest scales, in the voids between clusters of galaxies, where there are no strong forces binding things together. There, the stretching of spacetime dominates. This explains why our solar system, and even the Milky Way galaxy, are not being ripped apart by expansion. The gravitational binding of our galaxy is more than enough to resist the pull of dark energy on these scales. In fact, in a few billion years, our galaxy will collide and merge with the neighbouring Andromeda galaxy. Expansion won't stop this local drama, but zoom out far enough to the cosmic web of galaxies, and the large-scale pattern is unmistakable. Everything is drifting apart. The cosmic web is itself a fascinating structure. Galaxies are not scattered randomly through space. They form clusters and superclusters, connected by filaments of dark matter and gas, with vast voids in between. Imagine a three-dimensional spiderweb, where the threads are galaxies and the empty spaces are enormous voids. Expansion stretches this web, making the filaments longer and the voids larger. Over time, the web becomes more diffuse. The largest structures in the universe slowly drift apart. And yet, no matter where you place yourself in this web, the view looks similar. Every galaxy sees all the others receding. This is one of the great insights of modern cosmology. The universe has no preferred center. Expansion is uniform. The cosmos doesn't have a middle from which everything is spreading. Instead, it is the fabric of space itself stretching everywhere at once. But this leads us back to the nagging paradox. If the universe has no edge, no center, and no outside, then what does expansion really mean? To answer this, cosmologists define something called the scale factor. The scale factor is a number that describes how the size of the universe changes with time. If you imagine space as a grid, the scale factor is how much the distance between the grid lines has grown. At the moment of the Big Bang, the scale factor was 0. Today, it has some larger value. As time goes on, it increases, meaning distances grow. Expansion is simply the evolution of this scale factor. But expansion raises another question. What happens to energy as space stretches? After all, when light is redshifted by expansion, its wavelength increases, which means its energy decreases. Where does that energy go? The answer is subtle. In general relativity, energy conservation works differently than in everyday physics. Because space-time itself is dynamic, the concept of total energy isn't as straightforward. Instead, energy can be redistributed through the curvature of space-time. This is one reason cosmologists often describe expansion as stretching the energy budget of the universe in non-intuitive ways. Another way to probe expansion is through the concept of horizons. As we've mentioned, the observable universe has a finite size, about 46 billion light-years in radius. This defines what we can see, limited by the age of the universe and the speed of light. But there's also something called the event horizon. This is the boundary beyond which events will never be able to affect us, no matter how long the universe lasts. Because expansion is accelerating, galaxies beyond a certain distance will forever recede faster than light, meaning their light will never reach us. This event horizon defines the ultimate limit of our observable reality. In other words, the universe we see is not the universe that exists. Beyond our horizon, expansion continues. Entire realms of galaxies lie permanently hidden from us, carried away faster than light can cross the growing gulf of space. The true universe may be vastly larger, perhaps infinite, but we will never know for certain. Expansion makes parts of the universe forever inaccessible. Let's reflect on this for a moment. You are a conscious being, alive in a brief window of cosmic time, with access to a universe of 46 billion light-years across. You can see galaxies, stars, and light from nearly 14 billion years ago. But there are regions of the cosmos that you will never know exist. No telescope, no matter how powerful, could bring them into view. Expansion is not just a physical process, it is a limit on knowledge itself. It sets boundaries on what can ever be observed or understood. And yet, within these boundaries, expansion reveals an astonishing story. It tells us that the universe was once smaller, hotter, and denser. It tells us that time itself had a beginning. It tells us that what we see today is only a snapshot of an evolving cosmos. Expansion is not just a scientific fact. It is the reason we have a universe filled with galaxies instead of a hot, dense plasma. It is the reason we can look up at night and see a sky full of stars. But as always, new knowledge leads to deeper questions. If expansion is accelerating, what will the future look like? One possible outcome, as we've seen, is the heat death. In this scenario, expansion continues forever, stretching the universe until galaxies, stars, and even atoms decay, leaving a cold, dark void filled only with radiation. Another possibility is the Big Rip, where dark energy grows stronger over time and tears everything apart. A third is the Big Crunch, where expansion reverses and the universe collapses back into a singularity. Current evidence points most strongly to the heat death, but the story isn't finished. It's worth noting how strange it is that the ultimate fate of the universe depends on something we don't yet understand: dark energy. This mysterious component dominates the cosmos, yet we have almost no idea what it is. It could be a property of space itself, an energy of the vacuum. It could be the effect of extra dimensions or the dynamics of some unknown field. It might even change over time, altering the course of cosmic history. Right now, dark energy is the great mystery of cosmology, and it is dark energy that determines how the expansion unfolds. So here we are, beings made of atoms, asking what the universe is expanding into. The most rigorous answer is that it expands into nothing, because outside the universe has no meaning. The universe is everything, and its expansion is simply the increase of distances within itself. But as speculative as it may be, the possibility of a multiverse keeps creeping in. If inflation theory is correct, then our universe may be just one of many, each with its own expansion, its own physics, its own reality. If that's true, then perhaps our universe really is expanding into a larger framework. But until we find evidence, this remains a possibility at the edge of science. In the end, the expanding universe is both a scientific fact and a philosophical puzzle. It forces us to question the very concepts of space, time, and existence. It shows us that reality is stranger than intuition, larger than imagination, and deeper than human categories. It humbles us, reminding us that we are small creatures in a vast, mysterious cosmos. Yet it also elevates us because we have the ability to wonder, to ask, to seek. The expansion of the universe may be beyond our control, but the expansion of our understanding is entirely our own. When people first hear the phrase, "the universe is expanding," they often imagine a sort of explosion into empty space. It's natural. Our brains are wired to picture things in terms of inside and outside, of a center and an edge. But when we try to map those instincts onto the cosmos, we get lost, because the expansion of the universe doesn't work that way. It isn't an explosion in space, it's an expansion of space. And that subtle distinction changes everything. To really appreciate this, let's consider the analogy of a balloon. If you draw dots on the surface of a balloon and inflate it, the dots move apart. Each dot sees every other dot receding. Importantly, the surface of the balloon doesn't expand into the surrounding room from the perspective of the dots. It simply stretches. The balloon has no edge in 2 dimensions. Its surface is finite but unbounded. Now scale that up a dimension. Our universe may be like that balloon, except we live not on the surface, but inside the 3-dimensional volume. As it expands, everything within it moves apart. Not because it's rushing into pre-existing space, but because space itself is growing. This analogy, however, is still limited, because the balloon expands into the air around it. Our universe does not. There is no external room into which it stretches. Space and time are the framework of the universe, not something floating within a larger container. To ask what is outside the universe is like asking what is north of the North Pole. The question itself assumes categories that no longer apply. And yet, even as physicists insist that the universe is not expanding into anything, we still want to imagine it. We want to visualize what it means for distances to grow everywhere at once. That tension between mathematical precision and human imagination is where cosmology becomes not just science, but philosophy. One way to ground this discussion is to look at the actual evidence for expansion. The most famous comes from Edwin Hubble's discovery in 1929 that galaxies are receding from us, with velocities proportional to their distances. This relationship, now known as Hubble's law, is the first empirical proof of expansion. It showed that the universe is not static, as many once believed, but dynamic. Einstein himself had assumed a static universe when he developed general relativity in 1915. To make his equations fit that assumption, he added a fudge factor called the cosmological constant. After Hubble's discovery, Einstein reportedly called it his greatest blunder, though ironically, that same constant, or something very much like it, turned out to describe dark energy, the force behind the universe's accelerated expansion. Expansion also leaves an imprint in the cosmic microwave background radiation. This faint afterglow, discovered in 1965, is the cooled remnant of the hot, dense state of the early universe. Its uniformity across the sky is evidence that the universe was once much smaller and denser, and its tiny fluctuations are the seeds from which galaxies later formed. The very existence of this background radiation is only possible in a universe that expanded and cooled from an earlier state. More recently, expansion has been studied through Type 1a supernovae, exploding stars that act as standard candles. By comparing their intrinsic brightness to their observed brightness, astronomers can measure cosmic distances. In the late 1990s, these supernovae revealed something astonishing. Not only is the universe expanding, but the expansion is accelerating. This discovery, awarded the Nobel Prize in 2011, is the strongest evidence for dark energy. Without expansion, these observations make no sense. But beyond the evidence, the implications are profound. Expansion means the universe has a finite age. Rewind the cosmic clock, and galaxies converge. Temperatures rise, densities skyrocket. Eventually, you reach a point about 13.8 billion years ago when the scale factor was essentially zero, the Big Bang. Expansion is not just a feature of the universe, it is its origin story. Still, many people misinterpret the Big Bang. It was not an explosion in pre-existing space. It was the sudden emergence of space and time themselves. Before the Big Bang, there was nowhere for the universe to be. The Big Bang is the beginning of both space and time. That's a deeply unsettling idea, because it denies us the comfort of imagining a before. Cosmology forces us to let go of some of the most basic categories of thought. Expansion also challenges our sense of scale. On human timescales, it's imperceptible. The rate of expansion, described by the Hubble constant, is around 70 kilometers per second per megaparsec. That means a galaxy 1 megaparsec away, about 3.26 million light years, recedes at 70 kilometers per second. But since galaxies are tens or hundreds of megaparsecs away, the recession velocities add up quickly. At extreme distances, the recession speed surpasses the speed of light. This does not violate relativity, because it is not the galaxies moving through space faster than light, but space itself expanding. This distinction matters. No matter how fast expansion carries galaxies away, locally, nothing exceeds light speed. The laws of physics remain intact, but it does mean that vast regions of the universe are forever beyond our observational reach. They are not hidden because light travels too slowly, but because the fabric of reality itself stretches too quickly for light to bridge the gap. So what does this mean for the shape of the universe? According to Einstein's equations, the geometry of space is determined by its contents: matter, radiation, and dark energy. There are three main possibilities: closed, like the surface of a sphere, open, like a saddle, or flat, like a sheet. Current observations suggest the universe is flat, within a tiny margin of error. This means that parallel lines never converge or diverge on cosmic scales, and the overall geometry is Euclidean. A flat universe can be finite or infinite, depending on its topology. If it is infinite, expansion simply makes the infinite larger, an already difficult concept to wrap one's mind around. Another fascinating concept is cosmic inflation. In the first fraction of a second after the Big Bang, the universe is thought to have undergone a burst of exponential expansion, growing from subatomic size to macroscopic scale in less than a heartbeat. Inflation solves several puzzles in cosmology, such as why the universe looks the same in every direction and why it appears so flat. But inflation also suggests something else. If it happened once, it may be happening elsewhere. Some versions of inflation predict that new universes constantly bubble into existence in a larger multiverse. If that's true, then our universe really might be expanding into something, into a higher dimensional arena of eternal inflation. But this idea remains speculative. Let's pause and think about what this all means for us. The expansion of the universe is not just a distant, abstract phenomenon. It defines the horizon of what we can see and know. It sets the stage for the history of galaxies, stars, and planets. Without expansion, there would be no cosmic cooling, no stable atoms, no stars, no life. Expansion is the reason you exist, but it also defines your limits. You live in a universe where most of reality is forever out of reach. You are bound to a cosmic island, cut off from regions carried away by expansion. Even within the observable universe, time is finite. You can only see back so far. Beyond that lies a past and a future you will never touch. Expansion both creates and denies, both gives and withholds. There's a kind of poetry in this. The expansion of the universe mirrors the expansion of human understanding. We push our knowledge outward, building telescopes, launching satellites, probing the sky. And just as we glimpse the edges of what can be known, expansion pulls the horizon farther away. We are always chasing, never arriving. This raises an unsettling but thrilling possibility. Maybe our questions about expansion are unanswerable in principle. Maybe we will never know whether the universe is infinite or finite, whether it expands into a multiverse, whether it began with a singularity or a bounce. And maybe that's the point. The universe expands not only in size, but in mystery. Each answer creates new questions, and the horizon of our curiosity stretches with the horizon of the cosmos. When we left off, we were picturing the universe as a four-dimensional space where expansion doesn't mean things are flying apart into a void, but rather that the geometry of space-time itself is stretching. That's already enough to twist the imagination into knots. But now let's add another question that naturally emerges. If our universe is expanding, could it be just one bubble among countless others? And if that's the case, is it expanding into something larger, the multiverse itself? To answer, we first need to separate what we can observe from what we can hypothesize. Cosmology rests on evidence, the redshift of galaxies, the glow of the cosmic microwave background, the distribution of matter in vast cosmic webs. But beyond the edge of the observable universe lies the domain of speculation. This is where physicists allow themselves to ask bigger questions, not because they expect an immediate answer, but because those questions test the limits of our current theories. Imagine blowing soap bubbles in a sink. Each bubble has a thin film surface enclosing air. From the perspective of someone inside a bubble, if that were possible, you wouldn't see the sink or the other bubbles. You'd only experience your own enclosed space curved around you. The analogy isn't perfect, but it helps us imagine the possibility that our universe is one such bubble of space-time, with others floating beyond what we can see. The expansion we observe would then be the stretching of our bubble. But what about the space between bubbles? Does it exist in the way we think of space, or is it something more abstract? Physicists call one speculative idea eternal inflation. Inflation, you may remember, is the theory that in the first fraction of a second after the Big Bang, the universe expanded exponentially, far faster than the speed of light, smoothing out irregularities and giving us the large-scale uniformity we see today. Eternal inflation suggests that this process might not have stopped everywhere. While our patch of the universe exited inflation and cooled, other regions might still be inflating, creating new universes in the process. Each bubble universe would be like ours, or radically different, depending on the laws of physics that take hold there. If eternal inflation is true, then our universe isn't expanding into empty space, but into a larger multiverse, a constantly churning sea of inflating regions, each spawning their own universes. From our perspective, though, we could never see those other bubbles. The boundaries would recede faster than light, forever out of reach. So again, expansion would be internal to each bubble, not into a shared external space. The paradox softens. We're not expanding into something we can point to, but rather existing within a grander framework of inflating space-time. But there's another twist. Even if the multiverse exists, does it make sense to talk about the space between universes? Or is that an illusion of language? The trouble is, we always rely on analogies like balloons, bubbles, and surfaces to make sense of expansion. Yet these analogies still smuggle in the idea of an external container. They make us ask, what is the balloon sitting in? What surrounds the bubble? In truth, the mathematics of general relativity doesn't require such a container. Space-time is self-contained. It doesn't need a backdrop. The outside is a human invention, not a scientific necessity. Let's take a moment to slow down and think of this differently. Suppose you're an ant living on the surface of a huge, expanding balloon. For you, there is only the two-dimensional surface of the balloon. You cannot perceive the third dimension in which it floats. All you experience is that the distance between you and every other ant is increasing. To you, it feels as if space itself is stretching. From the outside, a human observer can say, the balloon is expanding into the room. But you, the ant, have no concept of the room. The room doesn't exist in your physical reality. In a similar way, we may never be able to perceive any room beyond our universe, if such a thing even exists. The key point here is that cosmology doesn't require an answer to what lies beyond in order to explain the data. The universe expands, galaxies drift apart, the cosmic microwave background cools. All of this can be described and predicted without assuming an external space. That's why many scientists are cautious about multiverse theories. They're fascinating, but currently untestable. And yet curiosity drives us to imagine. Let's follow that curiosity further. If there is a multiverse, and if each universe has its own physical constants, then expansion itself could take different forms. Some universes might expand faster than ours, others slower. Some might collapse quickly, forming failed universes where stars never ignite. Ours might be one of the rare successful bubbles that sustains complex structures, galaxies, planets, and eventually life. This brings us to the anthropic principle, the idea that we observe this universe because it is one of the rare ones that allows observers like us to exist. If the constants of physics were even slightly different, the strength of gravity, the charge of the electron, the rate of expansion, we might not be here to ask these questions. In this view, the multiverse solves one mystery: why our universe has the particular properties it does. But it also raises new mysteries. If there are infinite universes, does everything possible happen somewhere? And if so, does expansion mean anything beyond our local bubble? You might notice that every time we reach the edges of comprehension, language starts to buckle. We use words like into, outside, between, and beyond. But these words are forged in the furnace of everyday experience. They work fine for apples falling from trees or planets orbiting stars, but they grow slippery when we stretch them to cosmic scales. That's why cosmologists prefer to stick with the mathematics. Equations don't rely on metaphor. They describe what happens inside spacetime without requiring a stage beyond it. Still, it's hard to resist the question: what is the universe expanding into? Perhaps into nothing at all, because into is the wrong concept. Perhaps into itself, because space-time is dynamic and self-generating. Or perhaps into something unimaginable, a larger reality that we can only guess at, where our entire universe is a small ripple in an endless ocean. Think again of the night sky. Every dot of light is a galaxy, some with hundreds of billions of stars, and all of them are moving away, carried on the tide of cosmic expansion. Beyond what we can see, there are more galaxies, hidden behind the horizon of light speed. Beyond those, more still, perhaps endlessly. If we could lift the veil, what would we find? Another bubble? Or nothing at all, just the silence of mathematics declaring that outside has no meaning? Expansion forces us into humility. It reminds us that we are bound by the limits of observation, yet our minds constantly reach further, demanding to know. This balance between evidence and imagination is the essence of cosmology. On one hand, we measure, calculate, test. On the other, we wonder, speculate, and dream. Both sides are necessary because the universe is not just a set of equations, it is also the mystery that inspires us to ask. As we move deeper into this paradox, it's worth pausing to consider. Maybe the universe doesn't need to expand into anything, because it already contains everything. The whole of space and time, the laws of physics, the fields and forces, all self-contained, without edges. If that's the case, then the expansion is not a journey outward, but an unfolding inward, a continuous creation of space itself. And yet, for all our scientific confidence, the possibility of a multiverse lingers. It may remain forever unprovable, but the idea itself shapes how we think. It challenges us to see our universe not as the only reality, but as one chapter in a much larger story. Whether that story exists or not, the fact that we can conceive it at all is remarkable. It shows that the human mind, though confined to a small planet in a modest galaxy, is capable of grappling with infinite possibilities. We've been circling the heart of this question. What is the universe expanding into? Up to this point, we've explored how the universe has no edge, how geometry itself is shaped by the expansion, and how dimensions beyond our perception might provide clues. But now, let's take a deeper look into some of the more daring possibilities scientists and philosophers have proposed, especially when we allow ourselves to ask, could our universe be part of something larger, something like a cosmic neighborhood? And if so, what lies outside the neighborhood walls? The first big idea here is the multiverse hypothesis. Imagine that what we call the universe is really just one bubble among countless bubbles, each with its own laws of physics, perhaps expanding within some vast backdrop of space. This idea has been fueled by a few different lines of reasoning. One comes from eternal inflation. the idea that inflation, the runaway ballooning of space-time that occurred in the first fraction of a second after the Big Bang, didn't just happen once in one place. Instead, it may be constantly occurring in different regions. In each of these regions, a bubble-like universe could form, inflating rapidly and then cooling into something like the universe we live in. If that's true, our expanding universe might not be expanding into nothing, but rather into an inflating background that itself spawns other universes. But before you picture bubbles floating inside some pre-existing air, it's important to clarify. These universes don't exist in the same space. Each bubble carries its own space-time. The between isn't space as we know it. Instead, it's an abstraction, something we can't directly picture, since all of our intuitions about outside come from within our own bubble. So if our universe is one among many, it doesn't expand into the others. It's self-contained, stretching within its own space-time, even as new universes form elsewhere. Now let's zoom in on another possibility, that the universe is infinite. If space is infinite, then asking what it's expanding into may not even make sense. Expansion, in this case, is less about stretching into something and more about the changing scale of distances. Galaxies move apart not because they're traveling into a new void, but because the metric that defines distance is stretching. An infinite universe can expand forever without needing an outside because every point within it moves relative to every other point. It's as if you were standing on an endless grid painted on a rubber sheet, and the rubber keeps stretching. The sheet doesn't need an edge. It already fills everything. Yet the distances on it grow large over time. And yet, even here, the mind rebels. Infinity is not something our brains grasp easily. When we ask, into what is it expanding, we're trying to reconcile our sense of bounded objects with a reality that might have no boundary at all. But scientists remind us, infinity is a feature that mathematics handles more comfortably than our imaginations do. The equations describing expansion don't require an outer container. They only require the rules of geometry and the passage of time. Still, let's consider a more radical view. Could the universe be expanding into itself? That sounds contradictory, but think of this. If space is curved in a higher dimensional way, then the expansion might simply be the stretching of that curvature. The fabric doesn't need an outside, just as the surface of Earth doesn't need an extra dimension for its shape to exist. But when we talk about curvature in 4 dimensions, it could allow for a strange reality where the universe folds back on itself. Some models even suggest that if you traveled far enough in one direction, you might eventually return to your starting point, much like circumnavigating the globe. In this kind of finite but boundless universe, expansion doesn't push into new territory. It changes the internal scale, so the journey around the loop becomes longer and longer. There's also a daring, somewhat philosophical idea that the universe is expanding into a realm of pure possibility, a mathematical landscape of all potential realities. In this view, space-time itself is like a structure emerging from deeper, abstract laws. The outside of the universe wouldn't be a place, but a set of conditions that allow the universe to exist in the first place. Here, the expansion becomes less a physical motion and more a kind of unfolding, as if reality is gradually revealing itself according to the rules built into its foundation. Let's not forget dark energy. This mysterious force is driving the acceleration of expansion. We don't know what dark energy is, but it may offer clues about the where of expansion. Some theorists suggest it's not so much a force pushing outward as it is an inherent property of space itself. If that's the case, then as new space is created through expansion, dark energy fills it uniformly, ensuring that the expansion accelerates rather than slows down. This means that instead of asking, what is the universe expanding into, we might better ask, what is it expanding with? And the answer may be, it's expanding with dark energy, with vacuum energy, with the very stuff of space-time itself. We should also consider the possibility that the question itself is flawed, an artifact of how human perception works. Our brains evolved to understand movement of objects in space, but cosmology deals with something stranger, the evolution of space itself. To us, the universe looks like a thing, and things must expand into something. But the equations of general relativity don't demand an external arena. Space grows internally, and that's enough. It's possible that outside the universe is simply not a meaningful concept. That said, curiosity has always pushed us to challenge even the seemingly meaningless. So let's indulge in a thought experiment. Imagine our universe like a balloon, not inflating inside a room, but inflating in a realm where there are no directions, no up or down, no left or right. You can't point outside the balloon because directions only exist within the balloon's surface. Expansion, then, doesn't move into a new space. It generates more surface. Translating that to our cosmos, expansion generates more space-time. There's no edge to cross, no container to reach. Just a continual increase in the distances between points. Now imagine something more mind-bending. What if expansion isn't happening into space, but into time? Some models of cosmology suggest that as the universe expands, it's not just creating more spatial separation, but also more temporal moments. In this interpretation, outside the universe isn't another place, but another time. A future that doesn't yet exist, but which becomes real as the universe grows. This transforms the question from what space is it expanding into to what future is it expanding into. That future may be just as mysterious as any hypothetical external dimension, but it's also intimately tied to our own existence. And finally, there is the ultimate possibility that the question will never be fully answered, not because it's meaningless, but because it touches the limits of what beings inside a universe can know. If space-time defines all experience, then outside space-time is forever beyond direct measurement. Still, the paradox serves a purpose. It forces us to expand our own mental universe, to loosen the grip of everyday assumptions, and to sit with mystery as part of knowledge. So, is the universe expanding into something? Maybe it's into itself, maybe into infinity, maybe into a higher dimensional framework, maybe not into anything at all. The paradox lies in the fact that all these answers feel incomplete, but together they sketch a picture. The universe doesn't expand into space, it expands space itself, and that realization may be as close as we can get to resolving the puzzle, while still leaving room for wonder. To really feel the weight of this question, let's rewind to the moment of the Big Bang itself. At that time, about 13.8 billion years ago, all of space, all of matter, and all of energy were concentrated in a state of unimaginable density and heat. The common mistake is to imagine this as an explosion that happened at a single point in pre-existing space, scattering matter outward into emptiness. That's the picture our minds naturally paint. But cosmologists are emphatic. The Big Bang wasn't an explosion in space. It was the expansion of space itself. Every point in the universe was once compressed into that early state, and every point has been expanding ever since. So when we ask, what's the universe expanding into? We may be carrying a false image of the Big Bang as a fireball inside a void. A better analogy is to imagine that all of space is being stretched everywhere at once. There is no edge where matter bursts into an external emptiness. The universe doesn't move outward into pre-existing nothing. It creates the stage as it grows. This is where the concept of cosmic horizons becomes crucial. Because the universe is finite in age, and because light has a finite speed, we can only observe a portion of it, the observable universe. It extends about 46 billion light years in every direction. But beyond that horizon, space continues. We can't see it, but according to the laws of cosmology, it's there, filled with galaxies, just like the ones we know. And those galaxies are also receding, carried away by the same expansion. So perhaps, instead of wondering what's outside the universe, the more meaningful question is, what lies beyond our horizon? In this way, the outside isn't a place beyond the universe, but a place beyond our sight. But even that answer feels temporary, doesn't it? Because if the observable universe is just a bubble inside a much larger cosmos, what contains that larger cosmos? We've returned again to the itch that won't go away. To scratch it, let's turn to some bold theoretical ideas. One is the possibility that our universe exists on a brane, a three-dimensional surface floating in a higher dimensional space, as proposed by string theory. In these models, our entire cosmos might be just one membrane in a vast, multi-dimensional arena. Expansion, then, would not be a stretching into nothing, but a stretching within this higher dimensional framework. Other branes could exist parallel to ours, each with its own universe. If that's true, then what lies outside our universe is not empty nothingness, but other universes stacked beside ours in ways we can't yet perceive. This leads naturally to the idea of cosmic collisions. If other branes exist, could they sometimes bump into ours? Some cosmologists have speculated that what we see as the Big Bang might actually have been the result of such a collision. Two universes brushing against one another in higher dimensional space, igniting a burst of energy that seeded our cosmos. If so, then the expansion of our universe isn't just a solitary event, but part of a larger cosmic dance. Another perspective comes from quantum cosmology. In this view, the universe may not need an external framework at all. Instead, it could emerge spontaneously from quantum fluctuations. Stephen Hawking and James Hartle famously proposed the no-boundary hypothesis, suggesting that the universe may be finite but unbounded. In their model, time itself curves smoothly into space, erasing the singular edge we call the Big Bang. In such a universe, asking what lies beyond is like asking what's north of the North Pole. The question collapses because the geometry of reality has no outside. But humans being humans, we're not satisfied with that. We want to press further. So let's imagine, even hypothetically, that there is an outside. What would it be? Some philosophers argue that if anything exists outside the universe, it must be of a different order of reality altogether, something beyond physical dimensions. That outside could be purely mathematical or purely informational. In fact, there are cosmologists who seriously entertain the idea that the universe itself is a kind of vast computation. If that's the case, then perhaps the expansion of the universe isn't a stretching of space, but the progressive running of a cosmic program, with new space generated as more of the code unfolds. What lies outside the universe in this model? The machine running the code, and that is something we may never access. Still, we can turn the question on its head. Instead of asking what the universe expands into, we could ask, what expands within the universe? On this level, the answer is clearer. It's not galaxies flying through pre-existing space. It's the metric of space-time itself increasing. The ruler by which we measure distances changes over time. That's why every galaxy sees every other galaxy receding from it. This also explains the famous analogy of raisin bread dough. As the dough rises, the raisins move apart, not because they're traveling, but because the dough itself is stretching. No raisin sits at the center. Every raisin perceives the others moving away. Yet here's where things get even stranger. If the expansion of the universe is accelerating, driven by dark energy, then in the far future, galaxies beyond our local group will recede faster than the speed of light. They'll slip beyond our cosmic horizon, leaving us in an isolated island of stars. From that distant perspective, future astronomers might conclude that their galaxy is all that exists. They'll never know about the vast universe we can see today. This means our current ability to even ask the question, what is the universe expanding into, is a fleeting privilege, a brief window in cosmic history when enough of the universe is visible to provoke the question at all. This brings us to an almost poetic conclusion. Maybe the universe is not expanding into space, but into understanding. Our grasp of the cosmos grows as we evolve theories, conduct observations, and push the boundaries of thought. Each time we think we've cornered the answer, the question unfolds into deeper layers, expanding not the universe itself, but our awareness of it. Let's pause and think of it this way. If the universe had an edge, we might imagine reaching it, crossing it, and finally answering the question. But if it doesn't, if it's infinite, unbounded, or fundamentally self-contained, then the real expansion may not be out there at all. It may be in here within the human mind, as we learn to hold paradox without needing to resolve it. And maybe that's the truest reflection of reality. Just as galaxies drift apart endlessly, our ideas too expand into new territory without ever arriving at a final border. We are inside a mystery that may never give up all its secrets, but the act of asking, of reaching, is itself part of the universe's expansion. Our wonder is woven into the fabric of space-time. We've travelled far together through this question, haven't we? At first glance, what is the universe expanding into seems like something a child might ask on a starry night. It has that simple, innocent quality, the kind of question that tumbles out without effort, but carries with it a weight that humbles even the most brilliant physicists. And as we've seen, the deeper we chase it, the stranger and more elusive it becomes. We began with the most common misunderstanding, the idea of the Big Bang as a conventional explosion, flinging matter into empty space. That's the image our minds instinctively create. But science gently corrects us. The Big Bang didn't happen in space, it was the expansion of space itself. Every point of the cosmos was once compressed into that hot, dense beginning, and every point has been stretching ever since. There's no fireball flying into a void. There's only the fabric of reality unfolding from within. And that leads to the first major revelation. The universe isn't expanding into anything. It doesn't need an outside. When cosmologists talk about expansion, they're describing the changing geometry of space itself. The distances between galaxies grow, not because galaxies are hurtling through a background stage, but because the stage itself is lengthening. Space is dynamic, not static, and we are woven into its flow. Yet even as we accept this, our minds rebel. How can something expand without expanding into something else? How can there be growth without an exterior? That's when cosmology invites us to think in terms of geometry. The universe might be finite but unbounded, like the surface of a sphere. You can walk around Earth forever without encountering an edge. There's no outside you can point to, even though the surface itself is limited. The same logic, extended into higher dimensions, suggests that our universe could be self-contained. Asking what lies beyond may simply be the wrong kind of question. But the human mind rarely lets go so easily. So we looked further into theories that suggest our universe may not be all that exists. Perhaps we are part of a multiverse, an endless froth of universes bubbling up from quantum fields, or countless brain worlds drifting through higher dimensional space. In such a vision, what lies outside our universe isn't emptiness, but other realities, each with its own laws of physics, its own galaxies, maybe even its own versions of us. The expansion of our cosmos might just be one chapter in a story far bigger than we can currently see. We then explored quantum cosmology, where the line between physics and philosophy grows blurry. Stephen Hawking's no-boundary proposal suggested that the universe may have no beginning and no edge, just as Earth has no edge at the North Pole. In this view, the universe isn't expanding into anything at all, because outside has no meaning. What we experience as time and space are self-contained. To ask what's beyond is like asking what's beyond the end of a circle. It's simply more circle. And still, the mind reaches further. If there truly is no outside, could it be that what the universe expands into is something more abstract, like mathematics or information? Some physicists argue that the universe is, at its core, a mathematical structure, unfolding as equations generate the fabric of space and time. In this sense, the expansion we observe may be a kind of computation, with each passing moment adding more output to the cosmic program. If so, what lies beyond our universe may not be space, but the deeper laws or meta-laws from which reality springs. Of course, we must admit the limits of our vision. The observable universe stretches about 46 billion light-years in all directions, but that's just the portion we can see. Beyond it lies the unobservable, vast regions forever hidden from us, because light hasn't had time to reach us. Are those regions infinite? Are they curved back into themselves? Do they dissolve into other domains with different constants of nature? We don't know, and maybe we never will. Yet there's something beautiful in that uncertainty. The very act of asking forces us to expand, just as the universe expands. Our concepts stretch, our language falters, our imagination strains, and in that stretching, we glimpse how deeply the question itself mirrors the cosmos. The universe isn't only expanding in distance, it's expanding in possibility, and so are we. Let's also consider time. Expansion isn't just a spatial story, it's a temporal one. In the future, as dark energy accelerates the expansion, galaxies will drift out of sight. Cosmic horizons will contract, and the universe will grow lonelier. Billions of years from now, distant astronomers will look out and see nothing beyond their local cluster of stars. To them, the universe will appear static, finite, empty of the grand structure we see today. Our cosmic vantage point is temporary, a gift of this particular epoch. Right now, the universe is open enough to provoke our deepest questions, but not yet closed off by the silence of expansion. And so maybe the answer isn't meant to be final. Maybe the question is less about solving a riddle and more about learning to live with wonder. When a child asks, "What is the universe expanding into?" the right response might not be a single explanation, but an invitation to keep asking, to keep stretching the imagination, to realize that the mystery is part of the design. Perhaps the truest answer is this: the universe expands into itself, into infinity, into futures not yet written, into the uncharted territory of both space and thought. For every new piece of understanding we gain, the frontier of unknowing rushes outward even faster. Just like galaxies drifting apart, our answers drift into new questions. In the end, maybe the real expansion is happening in us. We are the universe, become conscious, asking about itself. We are stardust pondering stardust, space-time folding inward to wonder about its own unfolding. The mystery is not out there separate, it is within us, woven into our ability to wonder at all.